In today's video, we will do unsupervised Landcover classification with kmeans in Python. We will load our bands, build a feature table, run kmeans, and visualize the classes. If this helps, please like, share the video, and also subscribe so you don't miss the next tutorials. Hey everyone, welcome back to Remote Sensing Pro. If you're new here, this channel is about breaking down remote sensing and GIS for beginners and researchers. Let's start by explaining how kmeans works. Kmeans is a simple clustering method, as we see right here. We have clusters of points. Let's say points, for instance. Each dot here is like a pixel with values from different bands, like different satellite bands, for instance. So we choose K, the number of clusters we want. In this example, we have 4 Ks. That's 4 clusters. 1, 2, 3, 4. Now, the algorithm starts by placing the red axis as cluster centers. Then repeats 2 steps. First is to assign each point to the nearest center. After that, the algorithm moves each center to the average of its points. It keeps repeating until the centers stop moving. In the end, every point here is grouped into one of the K clusters. And as you can see, each of the points currently has a cluster. We have the cluster that looks like blue color, we have the yellow, we have the purple, and then we have the green as well. In remote sensing, these clusters could represent water, bare soil, vegetation, or other land covers. The same idea applies to our multi-band image, just in more dimensions. If you would like to learn more about how kmeans works or different ways to choose the best K, please check out the official scikit-learn documentation. I'll put the link in the description below. Okay, now let's dive into coding. Alright, so we have our first step, as usual, which is to do a recap of band preparation, which we've learned earlier. And usually we import the glob, we import rasteria, we import numpy as np, and we create a folder that links us to the directory to the image folder we want. And we have the band files. We want to use it to fetch the bands that we want from the folder. All right, this is the simple step that we usually do. And one other thing I would like us to have a look at is a simple way to import your libraries without including all the imports. So if I run this code, for sure we don't have issues. It's going to go through. What it's going to do for us is to fetch the band 3, right? Okay, let's have a look at that first of all. Okay, you can see we have our band 3 because that's the band with the extension _B3, right? Okay, so I just want to show us that with or without importing 3 times, you can just do remove these imports and just use comma to import the 3 libraries once. So just do import glob for rasteria numpy as np, and that imports everything for you. So we can have a look at that one more time by just restarting the kernel. And let's run this again and see. You can see, so we have our crop image band3.t file ready for us. And so today we're going to use more than band 3, as we often do like band 3, band 4, or band 5. Usually we do 2 bands for calculating indices, right? Like NDWI and NDVI. But today we are running a kmeans algorithm and we need more bands. I'm going to remove this and add asterisk. Let's see. Okay, so with this asterisk, we'll be able to grab all the bands in this folder and not just band type. And that sort of helps us to see how many bands we have in the folder and how many bands we want to work with. Let's have a look. All right, so in this folder, we have 1, 2, 3, 4, 5, 6. We have 6 bands in this cropped image folder. And today we're going to use all of these bands to run the kmeans model. So know the number of bands that you have. So next is to read all bands and stack to the rows, the columns, and end bands, which is the number of bands. This we have done before, where we'll learn how to stack and visualize the true color and false color image. So if you've not checked that out, you just check out for, I think, tutorial 3. I'm going to add that link to the description below so you can check it out as well. Okay, so this will hold each band as a 2D array for us. So we have the array is equal to this. And we do the usual with rasura.open band files. We want to open these band files as source 0. So I'm choosing 0 as the first index. So the first band with index 0. Just use it to do georeferencing for us. You can use anyone, right? Anyone works. Just use one as a reference image and just georeference the rest of the images so they will be the same. And we do the transform equals to source 0.transform. So we are copying this transform from this first image to the rest. And we also use the CRS for this first image. And then we use the shape, dimension, height, and width, which is still the shape of this same image to be our rows and columns. Once we've georeferenced that, the next is for us to now open the image. So here we want to read each band as float.to and append the list. We're going to read each band into a 2D array. Convert to float.to. This is very important for safe math. And also numpy.nd stack, just to stack them. All right, let's have a look. Good. So we see here that our rows here, we have 3001 and columns 2001, and then we have 6 bands. So this corresponds to the number of bands we have. So this is a 3D image, 3-dimension, rows, columns, and bands. All right. Now this takes us to the next step, which is building feature matrix. And we're going to build the N by B, which is N pixels and B bands. Here, the first thing we want to do is to mask out the invalid pixels, and one of them is the NaN, and the second one is the infinite pixels. So we create valid equal to numpy.all, numpy.isfinite, stack that we have here, and axis 2. So this axis 2 is the bands. You see 0, 1, and 2, because we're starting with the index 0 as our first one, right? So this axis 2 is for the bands. So this is going to look into all the bands that we have in axis 2 and find every NaN values, pixel values, and also infinite pixel values and max them out. And this is going to create a 2D mask for us. All right. So the next one is we're going to now flatten the 3D that we have here into a 2D feature table that we name X. We're going to do that by X equal to stack.reshape. So we're flattening 1, 2, 3D image array into 2D feature table X, right? That's what we want to do here. The next is now, after we've done that, we're going to now flatten this mask. This mask that we've created here, we're going to flatten it into a 1D array, right? From 2D mask to 1D array. And then finally, we're creating this feature table with these flattened valid pixels. All right, so we've got our final one. I'm going to run this code and then we can check the shapes of what we have just done here. Okay, let me create more space. Let's have a look at the first one. The shape. Let's see the shape of what we created. So we can see the rows and the columns, which is same, right? So here we have everything that we need to be valid to be within a 2D mask that we created. And then the next is the X. Let's have a look at the X equal to start.reshape that we just reshaped. Instead of having rows, columns, and bands, we'll be expecting the number of pixels, which is rows and columns together, and then we'll have the bands. Let's have a look. So you can see that. So we've just multiplied rows and columns to have this. Let's just do it right here. Multiplied by this. You can see, so this is what we have here, right? And that gives us exactly what we're looking for. And now want to ensure that we're using the final valid flattened pixel that we're working with. And so to do that, we'll just check this final one, which will also give us the same 2-dimension as well. Awesome. So we still have our 2-dimension without any issues. And so what we did here was to flatten this first one, valid dot shape. Let's see the difference here. Valid dot shape is 2D, right? However, when we flattened it, what we have is valid flat dot shape. So when we flattened it, we now have the product of these two. So we have the 2D flattened to 1D. Now we're ready to standardize the bands before we can run the model. All right, let's have a look. Before we now go ahead to run the model, one more thing that we need to do is to just standardize each band so the scales are comparable. Each band will also contribute fairly. We're going to do that using the standardize, this z-score normalization. We want to ensure that one band is not contributing more because we're doing clustering, right? And we want to make sure that it's done fairly. For each of the band, we're going to grab one mean for each band. We have 6 bands, right? And then we're going to grab one standard deviation for each. And then we have also z-score for each. So this is going to be our last standardized pixel that we want to work with. And we can also confirm that the shape did not change even after we standardize it. We want to make sure we're still retaining the 2D array or the 2D feature table we want to work with. Let's confirm that again. Oh, that's an error because we did not run the code. So let's run the code first of all. And then now we'll run it. Now we can go ahead and do our clustering. So let's keep the code clean so we don't have any confusion. So next thing we want to do is to set up the model. Then we'll run the clustering on these standardized data. And so we need the kmeans that we're going to import from sklearn.cluster. This is just one library that you need and get things done. All right, so for a number of clusters, which you can label as K, right? We can just do K here and then we'll do K here. And that gives us everything we need. But we want to keep it as the number of classes because we're dealing with Landcover classes, right? And so we want to do 5. So we're choosing 5 classes for our Landcover. You can choose 10 or 2, depending on your study area. And so because I'm choosing 5, I have 0, 1, 2, 3, 4. So these are my 5 classes, right? And then we have the kmeans. So we have the kmeans number of clusters to be 5 that we have here. And then we have the random states to be 42. And we set our number of initialization to be 10. This runs kmeans 10 times with different initial guesses and then keeps the best solution. We have the labels to be kmeans.fit predict xz. This very xz we're working with, right? So we're not changing that. So once fit predict to assign a cluster ID to each valid pixels, all right? Each valid pixels. And both feeds the model and returns cluster assignments. So I'm going to run this model. And then I'm going to run the labels. Okay, let's wait for the model to finish and then we'll continue. Good, so everything is good. The model went through and that was done on the standardized data. Next we want to do is now make a full label array with -1 for no data. Okay, so we have the full labels and then we have our shape. We have -1 to be the node data. And then we have these on the valid flat. That remember, we have our valid flat here. Okay, and we are going to put the labels back into the image. We have the Landcover equal to labels full dot reshape the rows and the columns. Okay, right? Let's run this code. Okay, so everything went well. Now we want to do the final work, which is to visualize our result. Okay, to visualize the result, one thing we need to do is to use a matplotlib.pyplot as PLT, right? This is our usual visualization library. And we've used matplotlib.colors import listed color map, right? This helps us to kind of customize the colors we want to view, right? We've done that a couple of times. And because we have 5 classes, 5 number of classes, you're going to give colors to those classes, right? So that when you run the code, it will show you those classes. The first is white. You can randomly put any color because you don't know what's going to pop up. But when you look at your feature, you can choose to change the colors. So just randomly put colors like white, light blue, orange, light green, blue. And so we use our usual fixed size, 6 by 6. And for the Landcover that is -1, we want to remove it from our plot. So we're setting it to numpy.nan. And then we have our CMap color to be the CMap that we just customized here. And our vmean is 0. This is important. So our minimum is 0 because our minimum index class is 0. And our maximum is the number of class -1. So our number of class is 5. And when you remove 1 from 5 is 4. So that gives us the index for our number of class. So we have minimum 0, maximum 4, which is 5 minus 1. Okay, you can just put maximum 4 here. But sometimes it's good to automate it just in case you change this to be 7. And then you have 4 here. It's going to mess things up for you. But when you automate it by giving it number of class -1, anytime you change this, it's not going to affect your map visualization. Okay, and now you want to save it. So I want to save mine as kmeans underscore map. And DPI, I'm going to set to 300 as usual. And then BB box inches, I want to make it tight. And then finally, we want to do PLT to show. This is our usual way of plotting and saving, right? So let's go ahead and visualize our map. Okay, so this is our map, our kmeans clustering result. This is our kmeans classification result. And let's say that this watercolor, maybe it looks good, but I do have my best color. Give me a second. So I love this blue to be my water, so I'm gonna copy this. I don't have it of me, but that's my best. I'm gonna put this here. That's light blue, right? So I'll just put it here. Good. Here we go. All right, so I love this color a lot because it kind of gives me that feel of how ocean should be like. I know not all the ocean color is like this, right? But I just love this blue color. And so we have our final result from our kmeans classification. We have the ocean water as classified using this color that I like a lot. And we have the blue color here, which is likely going to be maybe still water, right? And then we have the white. These white areas represent the built up areas or urbanized areas where we have constructions or something like that, like housing constructions. And we have the vegetation area or forested areas. As you can see, these ones are in one category. We also have orange. Orange is another feature that is happening right within this forested environment. We just worked through unsupervised land cover classification with kmeans in Python. We loaded our bands, reshaped them into a feature table, standardized the values, ran kmeans, and also visualized the clusters as a land cover map. So the key part is choosing K, the number of clusters you want, like we just did here, right? Is very important to know the number of classes that you want. That choice controls how many land cover groups kmeans will separate for you. Maybe water, for us, vegetation, bare soil, or even more detailed classes depending on your data. So now you know how to build a full unsupervised classification workflow from scratch in Python. If you found this useful, please like, share, and subscribe so you don't miss the upcoming tutorials in this series, okay? I will see you in the next one.